Okay, so this is the next lecture. So I want to talk about the randomized complexity of disjointness, right? So we have seen the deterministic complexity of disjointness, which is linear n plus one, and we have already seen a couple of places where we use that the randomized complexity of disjointness is linear, right? So here will be we will actually show a randomized, but we have not really seen randomized lower bounds on disjointness, and this will be the first. This will be the first place where we'll see that the randomized lower bound for disjointness, right? The lower bound that we will explain in today's lecture and in the next lecture will be not linear, but it will be square root n. Yeah, so first we will see this, and this was a result by Babai-Frankl and Simon in 1986, right? Okay, so as I was saying in the previous lecture, this uses the distributional complexity. So we already saw that the randomized complexity using public randomness is equal to the maximum distribution complexity. So, and we also saw that under uniform distribution, the disjointness has a very low complexity. In fact, we don't need we don't need to communicate anything. We could just because most of the input pairs are not disjoint, right? So the fraction of ones are. So we also saw that the fraction of there are 3 power n ones in the disjointness matrix out of 4 power n entries. So as n increases, this becomes very small. So the parties Alice and Bob could just guess that guess that their inputs are not disjoint, and they will be correct with high probability, right? Depending on it. So uniform distribution is not a very good choice of the distribution. Let us see what, but we will find, we'll use another distribution which is not uniform distribution, and we'll show that under this distribution, the distributional complexity is at least square root n. Okay, so we already saw during one of the physical meetings, we saw that if we set each bit in x and y, if the probability of each bit being 1 is 1 by square root n, then what is the probability that in an index I, both x and y are both xi and yi, both bits xi and yi are 1, it is 1 by n. What is the probability that both xi and yi are both not 1? So it is 1 minus 1 by n. And what is the probability that x and y are disjoint? It is a probability that at each index xi and yi are both not 1. Right? So this is 1 minus 1 by n, the whole power n, which is roughly 1 by e. So this gives us a constant probability that x and y are disjoint. So if each bit of x and y, if under the uniform distribution, each bit of x and y are set to 0 or 1 with equal probability, that is half. Now, if we tweak that and make each bit equal to 1 with probability 1 by square root n and 0 with the remaining probability, then we are seeing that the probability that two random strings x and y are disjoint is constant, which is 1 by e. It is independent of n. So this gives us a hint towards what distribution is required, right? So in the Babai-Frankl-Simon theorem, we will use a distribution that is inspired from this, right? This is a formal statement of the theorem. The theorem statement is that the randomized complexity of disjointness is at least square root n. Okay, so let us see the intuition. Any distributional complexity protocol, right? Must partition the matrix into almost monochromatic rectangles, right? Because we cannot make an error more than epsilon. So we will first show that. In fact, in today's lecture, we will show that any almost monochromatic rectangle must be small. Okay, so what is almost monochromatic and what is small, we will quantify in the the next lemma formally. And since each of these monochromatic rectangles must be small, any protocol must have a large number of rectangles. And because it has a large number of such rectangles, the protocol has to be, the complexity of the protocol also must be large. And that gives us a lower bound. Okay, so today we'll just see this lemma, or in fact we'll not see the entire proof, but we'll skip some details which we'll see in the next lecture. We'll see the proof of the lemma that states that any almost monochromatic rectangle must be small. Okay, so before that, what is the distribution that we are going to use? So we are going to use a product distribution. What do I mean by product distribution? So both Alice and Bob gets to pick a vector, right? Now the distribution is going to be a product distribution, means Alice picks her vector with some probability, Bob picks his vector with some probability, and the joint probability is just the product of this. So both of this happen independently. In fact, both of them have the same distribution over their own inputs. What is the distribution? So Alice and Bob are going to pick a vector which has exactly square root n ones, and the rest of the entry is 0. Okay? And there are n choose square root n such vectors that have square root n ones and the rest of them 0. And out of these n choose square root n possibilities, Alice is going to choose her vector with a uniform probability. So basically, out of Alice is going to choose any one of the vectors with the same probability. Any one of the vectors that has exactly square root n ones. Exactly square root n ones. Not more, not less. So since there are n choose square root n vectors, each one of them is going to be picked with a probability of 1 divided by n choose square root n. And if it has more ones or less ones, it is not going to be picked. It's going to be picked with probability 0. And Bob also will pick his vector y with exactly the same process, right? If it has exactly square root n ones, then it is going to be picked with probability 1 divided by n choose square root n and 0 otherwise. Fine. Basically, out of all the vectors with exactly square root n ones are going to be picked uniformly, and anything that has more or less ones are not going to be picked. So just to get an idea, again we saw an intuition, but there's yet another intuition. It's roughly the same thing actually. What is the probability that a randomly picked, and so mu is the probability that mu is a distribution. So Alice has her distribution, Bob has his distribution. In fact, they're the same, they're identical, and mu is the product distribution. So according to this distribution, what is the probability that x and y are disjoint? So maybe it's easier to think, let's say x is fixed. Now what is the probability that y is going to be disjoint with that x? One way to think is, now y could pick any vector that has exactly square root n ones. So what is the number of vectors that have exactly square root n ones? And out of all those vectors, what is the fraction of vectors that are disjoint with x? So roughly there are n minus square root n entries if you exclude x1 entries. So there are n minus square root n entries, out of which we have to choose square root n entries. So it will be roughly a binomial coefficient n minus square root n choose square root n, and out of n choose square root n. So instead of binomial coefficients, I'm just approximating with n minus square root n power square root n and n power square root n, which amounts to a constant, right? 1 minus 1 by square root n whole power square root n, which is 1 by e. So again, this is just an indication that things are going to be all right. Okay. Now let us go to lemma 1, which is the formalization of what I said earlier. Any almost monochromatic rectangle is going to be small, right? Okay, so let me formally state. So what is going to be? So instead of almost monochromatic, I'm going to have use another terminology called almost epsilon unbalanced one rectangle. Okay. So what does it mean? It means that um, if R is a one rectangle, which means the protocol is going to declare one, and what is the probability that once suppose x and suppose we pick an entry of R, so we given that the entry that we pick is within R, what is the probability that the this entry corresponds to a zero entry, right? So given xy in R, what is the probability that x and y are not disjoint, right? So it's a zero entry. So now, if the probability of this is less than epsilon, it's called an almost epsilon unbalanced one rectangle. So it is a one rectangle as per the protocol. What is the probability that what is the probability of a randomly picked entry within that rectangle is a zero entry. So in other words, roughly zero. We don't want more than zero epsilon fraction of the entries in that rectangle to be zero entries. Right? So I think there is an error here in the next line. Mu r intersection disjointness inverse of zero, the inverse of the function, should be at most epsilon times mu r. So there should be an epsilon here before mu r. I'm not writing this. I'll try to write. I'll try to see if I can add that when I share it, or just recall it when you see it. So just to call out the typo again, mu of R intersection disjointness inverse zero should be at most epsilon times mu R. Or this is also a formal definition. Given that x and y are chosen from the rectangle, what is the probability that it's a zero entry? This should be at most epsilon. This is called an almost epsilon unbalanced one rectangle. Right. So ideally, in a deterministic algorithm, deterministic protocol, we want epsilon to be zero. We don't want to allow any error. But here we are allowing some epsilon. Suppose R is an epsilon unbalanced one rectangle, then either the size of R is S cross T. So either the number of rows, that is S, or number of columns, that is size of T, is at most 2 power minus C square root n times n choose square root n. So let us just see this once again. So what are the entries that matter in the entire matrix? So the entire matrix we know is a 2 power n by 2 power n matrix. But since our distribution is only going to be between those, so our distribution is it has only non-negative weight or non-zero weight only on those entries that have exactly square root n once. In effect, what we have is a n choose square root n cross n choose square root n matrix. It's a matrix. So the matrix that matters to us is n choose square root n cross n choose square root n matrix, right? So it has n choose square root n rows and n choose square root n columns. So what is being said here is that any epsilon unbalanced one rectangle has either at most 2 power minus c square root n times the total number of rows, or the same 2 power minus c square root n times the total number of columns. So this much fraction of the total number of rows or columns, right? So the intuition is that if it's an almost epsilon unbalanced one rectangle, then either the number of rows is small, is 2 power minus c square root n fraction of the total number of rows, or 2 power minus c square root n fraction of the total number of columns. So this is the key thing here, right? This is what is going to be proved in lemma 1. Okay, so the proof of lemma 1. So you already seen the distribution and you already seen the statement. So even though the statement looks technical, it's not that hard. What is the idea of the proof? The idea of the proof is that if the number of rows is small, right? If the number of rows is small, then the lemma holds, right? Small meaning, again, this is just an intuition. Small meaning below the limit. Okay, just one more thing. The lemma states that there is such a constant C for which this holds. So if the number of rows is small, then the lemma holds. If the number of rows is not small, let's say it's beyond whatever is stated in the lemma 1, then the point is S is large. So then we will show that there are a lot of sets, because S is large, there are a lot of sets that are kind of disjoint within S itself. And because there are a lot of sets that are kind of disjoint, you can add these sets together to make a the union of these sets span a significant fraction of the universe. The universe is 1, 2, 3, 4 up to n. Okay, since these sets in S span a constant fraction of n, and we know that the elements in T, recall it's a one rectangle, right? It's a rectangle which the protocol is going to announce as a one rectangle. So the elements in T are almost disjoint with those in S, right? Or so we know that the elements in T, so it's all epsilon, almost epsilon monochromatic, or almost epsilon unbalanced one rectangle. So the elements in T are almost disjoint, and so that restricts where T can choose its elements from. So a constant fraction of the elements are in S. So the T has only the rest of the elements available to it. So the number of elements in T, or number of sets Y in T, is going to be small. So if S is large, the span of S is going to be large. So not many elements are going to be available to choose for T. So the number of sets in T are also going to be small. That's the idea. Okay. So let's go ahead with the proof. So that's the intuition. Let's go on with the proof. So suppose S is bigger than 2 power minus C dash, okay, not C, but C dash, square root n, n choose square root n. So C dash, what is C dash we'll come to later. But suppose S is bigger than this. Now we define S dash to be those sets X in S such that X intersects with at most 2 epsilon fraction of Y in T. Okay, so we have a rectangle S cross T. Now I am looking at a subset of S. A subset of S. What are the X that are going to be in that subset? The subset is called S dash. What are the X that is going to be in S dash? Those X that are going to, so you can look at each row and see how many fraction of those rows are going to be 1 entries, right? So the 0 entries. 0 entries are those that intersect with T, that are not disjoint with T. So I want the row to have at most 2 epsilon zeros, 2 epsilon fraction of zeros. Okay, I want the row to have at most 2 epsilon fraction of the zeros. If so, I will include it in S dash. Okay. The first observation is that size of S dash is at least half the size of S. Why is that? If the size of S dash is at most half of S, that means there are more than half the elements of S that are not in S dash. And why are they not in S dash? Because they contain more than 2 epsilon zeros in their rows. So they contain more than 2 epsilon fraction of the sets Y that they contain elements X that intersects with more than 2 epsilon fraction of Y and T. Now if you just look at these sets that intersect in more than 2 epsilon fraction, So we already have s by 2, at least s by 2 elements, s by 2 rows, and in each row we have more than 2 epsilon intersections. So overall, the s cross t rectangle, we have more than epsilon fraction, because 2 epsilon times s cross s by 2 is, the 2 cancels, and we have epsilon fraction of the entire rectangle. Epsilon fraction of the entire rectangle as s cross t is now 0 entries. But that's a contradiction to what we started with. We said that there are at most epsilon fraction of elements in R that are 0 entries. But now this gives you that there are at least epsilon, there are strictly greater than epsilon fraction, which is a contradiction. So this means that there are at most, or there are at least s by 2 elements in the size set S dash. And what is the property of the set S dash? Each row has at most 2 epsilon fraction zeros of those y in T. Right? Okay, let me go ahead. Okay, so now we will state a claim. Again, this proof of this claim will be proved in the next lecture. So first I will state the claim. The claim is that there exists a C dash. Okay, so the C dash is going to come from this claim, even though we stated C dash here. There exists a C dash such that if S dash is going to be greater than half 2 power minus C dash square root n, and choose n square root n, then for k equal to square root n by 3, so I'm just using k because it's easier to write. Right? There exists sets x1, x2 up to xk in S prime or S dash, such that the property is that for each I, the intersection with all the previous xj's. So you take x1, that's fine. So let's say you take x10, and then now you look at how many of the elements of x10 are already covered in x1 to x9. And what we are saying is that at most half of it are covered. So recall, all of this sets x have exactly square root n elements. And what we are saying is that if you pick an xi and look at how all the previous xi, how many elements in xi are already been covered. And we want it to be at most square root n by 2. That means, let's say we are building up this union x1, x2, x3, x4, x5, etc. We are taking the union of all of this. When you take x1, all the elements are new. When you take x2, there are at least square root n by 2 new elements that are not covered by x1. When you take x3, there are at least square root n by 2 new elements that are not covered by x1 and x2, and so on. Let's say you take x10, then there are at least square root n by 2 new elements in x10 that are not covered by x1, x2, x3 up to x9. So now what this gives you is that if you take all these sets together, x1 to xk, we have a lower bound on how many elements these together have. Right? Because every set xi brings at least square root n by 2 new elements. So now, since S dash that we stated here has size at least S by 2, right? Now it contains, by the claim, I'm not going to prove the claim now, we'll prove the claim later. S dash has a subset S double dash x1 to xk, such that if you take the union of these elements, each new x brings in square root n by 2 new elements. And how many elements are there? Or how many sets are there? The number of sets is going to be k, and k is square root n by 3. So the total number of elements in the union of sets in S dash is going to be square root n by 3 multiplied by square root n by 2, which is n by 6. So this is what I referred to earlier. Now we are saying that if S cross T is epsilon, almost epsilon unbalanced, then S contains a subset S double prime or S double dash, such that the sets contained in S double prime together span n by 6 elements of the universe. So now most of T cannot use these elements, right? So now T cannot pick too much of these elements that are there in this union. So now T has to choose from the remaining, and hence how many ever T we can pick, it is going to be upper bounded by something, and that's what is going to happen in the rest of the proof. Okay, so now let us define a set called T prime or T dash, which is a subset of T. What is the property of T prime? T prime contains those Y that intersects with at most 4 epsilon fraction of sets in S double prime. Recall? So T prime consists of at most T prime consists of those Y that intersects with at most 4 epsilon fraction of sets xi in S double prime. Okay, we are only restricting to S double prime. What do we know about S double prime? S double prime is already a subset of S prime, and S prime, we know that each set X in S prime intersects with at most 2 epsilon fraction of Y in T. So if you look at the first claim is that T prime is at least half the size of T. Why is this? So consider the rectangle S double prime cross T. We know that each element in S double prime intersects with at most 2 epsilon fraction of Y's in T. Right? That's what, because they're all elements of S dash. So each element of S double prime intersects with at most 2 epsilon fraction of Y's in T. So the total fraction of intersections in the rectangle S double prime cross T is at most 2 epsilon times the size of S double prime times the size of T. But if T prime is at most half T by 2, then that means that more than T by 2 Y's intersect with a greater than 4 epsilon fraction of the sets in S double prime, and this gives you more than T times S double prime times 2 epsilon intersections in intersections in S double prime times S double prime cross T. And that is a contradiction to what I just said earlier, because each row has at most 2 epsilon fraction of zeros. So the total fraction of zeros also must be T times S double prime times 2 epsilon. But so this is a contradiction. And so it follows that the fraction of the size of T prime is at least T by 2. Okay. So we have S prime, which is at least S by 2, and within S prime we chose S double prime of size square root n by 3. Again, how we get S double prime is going to be proved later as proof of the claim. And within T prime, or within T, we have T prime which is of size at least T by 2. And now the property is that for any Y in T prime, Y intersects with at most 4 epsilon fraction of the sets. So now, because we saw that T prime is at least half the size of T, we want to eventually upper bound T, right? Because we have started with the assumption that S is large. Now we want to say that the elements in S, there are enough elements in S that span a constant fraction of the universe. So we want to say that the elements in T are not too many, because it can only choose from the remaining elements. Right? So instead of upper bounding T, we will upper bound T prime, and that will imply an upper bound on T, because T prime is at least half the size of T. Right? So any upper bound for T prime is, you multiply 2, you get an upper bound for T. So each y in T prime intersects with at most 4 epsilon fraction of sets in S double prime, or 4 epsilon k sets in S double prime. So let's see how many fraction of for a fixed y, there are the remaining sets are disjoint from y. So remaining sets, the number is 1 minus 4 epsilon times k, right? So let us call these sets xi1, xi2, etc. xi subscript 1 minus 4 epsilon times k, which are disjoint from y. Now, so what does it mean? So y cannot choose any of the elements in these 1 minus 4 epsilon k sets, because it's disjoint. So how many elements can y choose from? The number of elements, so all these 1 minus 4 epsilon k sets, the elements inside that is out. Okay, so how many elements are contained in these sets? xi1, xi2, xi1 minus 4 epsilon k. We know by the property of the set S double prime, we know that each element each xi has at least square root n by 2 new elements. So there are 1 minus 4 epsilon k sets, and each set brings in square root n by 2 new elements, and where k is square root n by 3. So there are together we have 1 minus 4 epsilon times n by 6 entries spanned by xi1 to xi1 minus 4 epsilon times k. The number of entries is 1 minus number of elements spanned is 1 minus 4 epsilon times n by 6. So the remaining elements in the universe is what is available to choose for y, because y is disjoint with that. So the remaining is n minus this, and if you simplify, you get it as 5n by 6 plus 4 epsilon times n by 6. And let's assume that epsilon is small, let's say at most 1 by 100. And now you can easily do this calculation and see that this is at most 8 by 9 times n. So the universe that is available for you to choose the elements of y is limited to 8 by 9 times n. So only 1/9 of the entries in n are gone. So now let us just try to, that is enough for us. So it's a constant fraction, and that is enough for us to bound the number of elements of T prime. Let's see. So we started with the y in T prime. We know that it is a subset of these 8 by 9 n entries. Now let us see how many y's are possible. So what we said is any y, there are at least 1 minus 4 epsilon set times k sets in S double prime that are disjoint, right? So how many ways, and this could change. The first y could have a different 1 minus 4 epsilon times k sets that are disjoint. The second y could have another set of sets that are disjoint, and so on. So given the k sets in S double prime, how many ways can you choose the 1 minus 4 epsilon times k sets that are disjoint? Again, another way to see it is how do you choose the intersecting sets that are 4 epsilon times k sets? That is given by choose 4 epsilon k many ways. Once you pick the intersecting sets or disjoint sets, how many ways you can choose the remaining elements of y? So we know that by the calculation that we just performed, 8 by 9 n fraction of elements is all that is available to y, and from that you have to choose square root and entries. Okay, so we have this. So now replacing k with square root n by 3, you get this and this. So we first choose the number of which are the sets that are disjoint with y. And that you can do in k choose 4 epsilon k ways. And once you've chosen that, you have excluded at least 1 by 9 n entries. Out of the remaining at most 8 by 9 n entries, you have to choose square root n entries, and you can do that in this many ways. And this is a upper bound on the number of elements that T prime can have. And the thing is, using what is called Stirling's approximation, you can upper bound it with 2 power minus 1 minus c double prime square root n times n choose square root n. So recall that there are n choose square root n possibilities for the number of columns, and T is a subset of that, T prime is another subset of that. Now we are saying that T prime is at most 2 power minus 1 minus c double prime square root n fraction of the total number of columns. Right? That's what we are saying. So now we'll first complete the proof. We'll just leave the Stirling calculation for a bit. We'll first complete the proof. So recall what we did. We assumed that S is large, and assuming S is large, we have shown that T prime is small. Okay, now we had C prime. We assumed that S is greater than 2 power minus C prime square root n fraction. So first let us set C to be the smaller of C prime and C double prime. C prime comes from the claim, C double prime comes from the Stirling's calculation. So whatever it is, we choose C to be the smaller of that. Both of them are constants. Now, if size of S is at least 2 power minus C square root n fraction of the entire number of rows, then since C is smaller than C prime, and since there is a negative sign, then size of S is at least 2 power minus C prime square root n as well. So C is smaller than C prime. So S is greater than 2 power minus C means S is greater than 2 power minus C prime. Right? So if S is greater than this, then S is greater than this as well. This means that by all the calculations that we have done till now, size of T prime is at most 2 power minus 1 minus C double prime square root n fraction of the entire number of columns. So instead of 2 power minus 1, I'm just writing it as half times 2 power minus C double prime square root n fraction. So now size of T prime is at least half of size of T. So size of T is at most 2 times size of T prime. So that this half goes away. 2 power minus C double prime square root n fraction. And since C double prime is at least C, we can get that this is at most 2 power minus C square root n choose square root n. So if S is bigger than 2 power minus C square root n fraction, then T is smaller than 2 power minus C square root n fraction. So either S or T is smaller than 2 power minus C square root n fraction. So at this point, what we have left out, and this completes the proof of the lemma. At this point, what we have left out is the Stirling's approximation calculation and the proof of the claim. So the proof of the claim I will prove it in next class, and Stirling calculation we will do after a recap of the lemma. Okay. So the statement, the lemma states that we first use the distribution. We select all. We are only Alice and Bob are going to pick x and y that have exactly square root and ones, and amongst these x and y that have exactly square root and ones, they choose every vector with equal probability. That means each vector is going to be chosen with probability 1 divided by n choose square root n. It is the same for Alice and Bob. And mu is the distribution that results because of this process. And the lemma is that there is a constant C such that if R is an almost epsilon unbalanced one rectangle, which means R is a one rectangle that has at most epsilon fraction of the entries as zeros, then either S or T is at most 2 power minus C square root n fraction of the total possible rows or columns. Okay, the idea is if S is small, then the lemma holds. Otherwise, S is large. So we show that S contains some elements that span some fraction of the universe, and then T is restricted from choosing the remaining elements of the universe, and that limits the size of T. So we first assumed S is greater than this, and then we looked at S prime, which is a set of all elements X in S that intersects with at most 2 epsilon fraction of sets Y. Or when I say intersects with, means it's not disjoint. So this corresponds to 0 entries in the matrix. So notice that even though we are using a product, we are using not the uniform distribution. It is, you can think of it as a uniform distribution inside the inside the choice that is being made by Alice and Bob, inside the choices that are available to Alice and Bob, right? So we choose n choose square root n rows, n choose square root n columns, and we restrict to this submatrix of M, and inside this all the possibilities are uniform. So it is okay to now talk about fraction of entries, etc., because we don't have like biased distribution within that n choose square root n rows and n choose square root n cross n choose square root n submatrix. So we can talk about fraction, and it will be fine once we are within that. So first we let X be the S prime be the set of all X that intersects with at most 2 epsilon fraction of sets Y and T, or in the S cross T submatrix, these rows, those rows that have at most 2 epsilon fraction zeros, and if we argue that the number of such rows should be at least half the number of total rows, this is because if the number of otherwise there will be too many zeros in the entire submatrix, S cross T matrix. And then we use the if S prime is of that size, then it has a further submatrix S double prime, which is what is asserted by the claim here, such that the rows that are in S double prime are kind of, every row brings in a bunch of new entries. So every row brings in at least square root n by 2 new entries, and there are at least square root n by 3, there are at least square root n by 3 such rows. Which means that the elements in S prime, the union of that together forms at least n by 6 entries in the universe. Now we consider T prime. So recall that, okay, we consider T prime, which are those columns that intersect with at most 4 epsilon fraction of the xi in S double prime. So now you look at the columns of T and look at how many fraction of entries in S double prime it intersects with, and we pick only those columns that intersect with at most 4 epsilon fraction. So when I say intersect with, I mean not disjoint, or in other words, 0 entries for the matrix. Similar to the previous argument, we observe that size of T prime is at least half the size of T. Why is that? Otherwise, at least half the size of, at least T by 2 y's intersect with greater than 4 epsilon fraction of the sets. So there are at least 4 epsilon times T by 2 times S double prime fraction of zeros in the S double prime cross T sub matrix, which means T times S, size of T times size of S double prime times 2 epsilon zeros in S double prime cross T. But we know that S double prime is a subset of S prime, and we know that each row has at most 2 epsilon zeros. So together S double prime cross T should not have more than 2 epsilon fraction of zeros, because each row has 2 epsilon fraction of zeros. So this is a contradiction. So size of T prime is at least T by 2. Now we are going to upper bound T prime, and thereby we will get an upper bound for T. So each y in T prime intersects with, so what is the property of T prime? It intersects with at most 4 epsilon fraction. So it is disjoint with at least 1 minus 4 epsilon fraction of the sets in S double prime. So what are the remaining elements for it to choose? The remaining elements for it to choose are those that are not already covered. And we know that the elements in S double prime have this property that each set brings in at least square root n by 2 elements. So we do the calculation and we see that T prime, the y's in T prime have at most 8 by 9 possible choices. These choices may vary. The first y may have 8 by 9 n choices. The second y will have 8 by 9 n choices, which may be different from the first 8 by 9 n choices. The third y may have yet another 8 by 9 n choices. These choices will obviously intersect, but this could be different. Some element that is not available for the first y could be available for the second y, and so on. So what are the total number of y's? But this is enough for us. What are the total number of y's that are possible in T prime? So first, which sets in S double prime does that y intersect with? So there are 4 epsilon k such sets. So there are 4 epsilon k choose 4 epsilon k ways to choose that. And once we choose that, the 8 by 9 entries get fixed, or at most 8 by 9 entries get fixed. So that many entries are there for to choose as the entries of y. So that again another binomial coefficient, 8 by 9 n, choose square root n. And if you substitute k to be square root n by 3, you get that it is 2 power minus 1 minus c double prime square root n, fraction of the total number of columns. And if you set c to be minimum of c prime and c double prime, the rest of the argument easily follows. If s is bigger than 2 power minus c square root n fraction, then s is also bigger than 2 power minus c prime square root n fraction. This implies that T prime is at most half times 2 power minus c double prime square root n fraction, which means that T is at most 2 power minus c double prime square root n fraction, which means T is at most 2 power minus c square root n fraction. So either S or T is at most 2 power minus c square root n fraction of the total number of rows or columns. So that completes the proof, except for the two things, the claim and the Stirling's calculation. So the claim we will see in the next class. Stirling's calculation, I will just very quickly do it now. And it's just algebra, and you can verify it on your own. So the Stirling's approximation for the factorial, you can find references for this. I can provide some references in the lecture notes, is that m factorial is roughly square root of 2 pi square root m times m by e whole power m. And this holds with better accuracy as m grows, m tends to infinity, which is okay here because we are all talking about asymptotics here. So we had two things, right? Square root n by 3, 4 epsilon square root, choose 4 epsilon square root n by 3 and this, right? So we'll first take care of the first factor. So square root n by 3, choose 4 epsilon square root n by 3. So the thing to note is that this square root of 2 pi m is much smaller than something with the power m, so we'll ignore that. And then when you take a binomial coefficient, both the numerator and the denominator of the binomial coefficient, here is a factorial, right? Square root n by 3 factorial, here is 2 factorials, 4 epsilon square root n by 3 factorial and 1 minus 4 epsilon square root n by 3 factorial. But these two the numbers inside the factorial add up to the numerator. So the e power term will also vanish. So the only thing that we are going to consider is when you are approximating the binomial coefficient, we are only going to consider the m power m thing. So square root n by 3 gives you this, and the denominator as well. And I can cancel again now see that the square root n by 3 also cancels with the square root n by 3 available here and here. So we just have 1 by 4 epsilon times 4 epsilon power 4 epsilon power 4 epsilon and square root n by 3 and 1 minus 4 epsilon power 1 minus 4 epsilon square root n by 3. And now I can rewrite it as 2 power h of 4 epsilon multiplied by square root n by 3, where h is the so-called entropy function, where h of alpha is defined as minus of alpha log alpha plus 1 minus alpha log 1 minus alpha. So I'm just rewriting it. And this is a very popular, well-known thing, especially in information theory, the entropy function. And the property is that when alpha is between 0, it's studied when alpha is between 0 and 1. And this is maximized at alpha equal to half. When alpha is equal to half, then the value is 1. Everywhere else, the value is between 0 and 1. So it's like this. It's when alpha is equal to 0, it is 0. When alpha equal to 1, it is 0. And it increases from 0 to half and decreases from half to 0. It's symmetric about half, as you can tell from here. And the point I want to make is that when epsilon is small, 4 epsilon is also going to be small, and this number h of 4 epsilon is also going to be very small, very close to 0. So we'll come to that later. Now let us look at the next term, that is 8 by 9 n choose square root n. And in fact, we will take the n choose square root n in the right hand side and we'll compare it with that. Right? So what is 8 by 9 n choose square root n divided by n choose square root n. Again, like before, we write the m power m terms alone. So we have this in the numerator, and we have corresponding to n choose square root n, we have this. Now let us first cancel the square root n choose square root n. We do that. Then we have just 4 terms. So I write it like this. It's exactly the same things. I've not done anything else except for cancelling this. Now I take out n power n minus square root n from the numerator and write it here. And 8n by 9 power 8n by 9 minus square root n from the denominator, and I write it here. And what I have remaining, so once n is taken out, I have 1 minus square root n by n. The power remains the same. And in the denominator, I have 1 minus square root n divided by 8n by 9. The power is the same. And I have this over in the left side. The point here is that when n is large, this entire 1 minus things in the numerator and denominator are negligible. So I am going to ignore that. And what remains is this. So again, n is in the denominator, n power n minus square root n is there in the numerator. So the denominator what remains is n power square root n. And similarly for 8n by 9, what remains is 8n by 9 power square root n. And again, n can be cancelled. So what remains is 8 by 9 whole power square root n. Finally, we have we calculated this. I'm just confused. I think there is some mess up in the PDF file. So we first computed that square root n by 3, choose 4 epsilon square root n by 3 is at most this. And then we saw that 8n by 9 choose square root n divided by n by square root n choose square root n is at most this. So when you multiply that together, all three things together, I get this. And I can take this power square root n outside and I get this. And the point is that when epsilon is small, certainly h of 4 epsilon is also going to be small. And this will still be something, the thing inside the square bracket will still be something less than 1, a constant less than 1. And that power square root n. Now any constant less than 1, I can write it, I can take log to the base 2 and write it as 2 power minus 2 power minus some constant, and that's what we have done here. 2 power minus c double prime square root n. And okay, so there is this another matter of another half which is not difficult because that half is not multiplied by square root n. So this is something that I'm not going to show, but this gives you an idea of how the proof is. So that's it for today's lecture. I'll conclude now and I'll share the relevant material. Please go through this and please come prepared with discussion.